In question number 16, it is given that a metal rod moves at a constant velocity in a direction perpendicular to its length. A constant magnetic field exists in a space in direction perpendicular to the rod as well as velocity. Let's say rod is moving in this direction with velocity v. Magnetic field existing in this plane is perpendicular to the plane and inward. We have to select the correct statement. Here we know that due to the motion, the motional EMF will be created, that is E is equals to BVL. Here potential difference is created due to accumulation of charge. At this point positive charge will be accumulated and at this point negative charge will be accumulated. So inside the conductor the electric field from positive charge to negative charge will be created. So option 2 is correct option. In question number 17, a metallic rod of length L is tied to a string of length 2L and made to rotate with angular velocity omega. Let's say it is rotating about this point O. The length of string is 2L and the length of metallic rod is L. Let's say this is point of x is equals to 0. So this distance will be 2L and this distance will be 3L. We want to find the EMF induced. EMF is given by integration omega x into b dx. The EMF will induced from 2L to 3L, so limits will be from 2L to 3L. So E will be b omega by 2 into x square, limits from 2L to 3L. That will be b omega by 2 into 9L square minus 4L square. So EMF will be 5 omega b L square divided by 2. So option 4 is correct option. In question number 18, a flat circular coil having n turns is placed in a time varying magnetic field B is equals to B naught sine omega t. The outer radius of the coil is capital R. We want to determine the maximum value of induced EMF. Here E max is given by minus of d phi by dt. So E will be minus of d by dt of n a b is given by b naught sine omega t. So E will be minus n a b naught d by dt of sine omega t. The differentiation of sine omega t will be cos omega t. So E is equals to minus n a b naught omega cos omega t. We want to find the maximum value of EMF. For that the value of cos omega t will be minus 1. So E max will be n a b naught omega. Area is given by pi r square. So E max is equals to pi r square n b naught omega. So option 1 is correct option. In question number 19, a uniform but time varying field B of t exists in a circular region of radius a. We want to find the electric field variation at point P located at distance r from the center. Here from Maxwell's equation we can write integration E dot dl is equals to d phi by dt. So d by dt of BA, cos magnetic field and area vector are in same direction, so cos 0 is equals to E into 2 pi r. So this will be dB by dt, area will be pi a square is equals to E into 2 pi r. From this we can write E is directly proportional to a square by r. So E is inversely proportional to r. So option 2 is correct option. In question number 20, two inductors, each of inductance L, are joined in parallel. We want to find equivalent inductance. In parallel, equivalent inductance is given by 1 by L equivalent is equals to 1 by L plus 1 by L. So L equivalent will be equal to L by 2. So option 3 is correct option. In question number 21, a coil has 100 turns. When a current I is equals to 5 ampere, produce the magnetic flux of 1 microweber. We want to find the coefficient of self-inductance, that is L. Here N phi can be given as L into I, so L will be equal to N phi by I. N is given 100, phi is 10 power minus 6 Weber divided by current is 5 ampere. So L is 20 microhenry. So option 2 is correct option. In question number 22, two coils are at fixed locations. When coil 1 has no current and the current in coil 2 increases, so di2 by dt is positive and that is 15 ampere per second. The EMF in coil 1, that is E1, is 25 millivolt. When coil 2 has no current, that means I2 is 0 and coil 1 has current off, that is I1 is equals to 3.6 ampere. We want to find the flux linkage in coil 2. Here EMF due to mutual inductance is given by M di2 by dt, that is E1. So M will be E1 divided by di2 by dt. E1 is 25 into 10 power minus 3 divided by di2 by dt is 15. So M will be equal to 5 by 3 into 10 power minus 3 Henry. Now M can be written as phi 2 by I1. So phi 2 will be equal to M I1. M is 5 by 3 into 10 power minus 3 and I1 is 3.6. So phi 2 will be equal to 6 milliweber. So option 4 is correct option. In question number 23, the current in a coil is changed from 5 ampere to 10 ampere. So delta I is 5 ampere in 10 power minus 2 seconds. An EMF of 50 millivolt is induced in coil nearby it. We want to find the mutual inductance of the two coils. E can be given as M di by dt. So M will be E divided by di by dt. The EMF is 5 into 10 power minus 2 and di by dt is 5 divided by 10 power minus 2. So that will be 10 power minus 4 volt. So this is the mutual inductance, so it will be Henry. So it can be written as 100 micro Henry. Option 1 is correct option. In question number 24, a small square loop of wire of side small l is placed inside a large square loop of wire of side capital L. The loops are coplanar and their centers coincide. We want to find the mutual inductance of the system. The mutual inductance of the system is given by phi by I. So the phi is given by BA divided by current I. Here current is flowing through the loop, outer loop. So its magnetic field is directly proportional to 1 by L, and the area is taken of this square loop, so area is directly proportional to small l square. So we can write M is directly proportional to small l square by capital L. So option 2 is correct option. In question number 25, a coil of inductance 0.2 Henry is connected in series with a switch and a cell of EMF 1.6 volt. The total resistance of the circuit is 4 ohm. We want to find the initial rate of growth of current when the switch is closed. That means di by dt at t is equals to 0. Equation can be given by V is equals to L di by dt plus I R. But the moment when switch is closed at t is equals to 0, I will be 0. So we can write E is equals to L di by dt. So di by dt will be E by L. E is 1.6 divided by 0.2. That will be equal to 8 ampere per second. So option 4 is correct option. In question number 26, two inductance coils made of different metal wires are having same inductance. So L1 is equals to L2. Their time constants are in the ratio 1:2. So tau 1 by tau 2 is equals to 1:2. We want to find the ratio of their resistances. The time constant for LR circuit is given by L by R. As inductance is constant, we can write tau 1 by tau 2 is equals to R2 by R1 is equals to 1 by 2. So R1 by R2 will be equal to 2. So option 4 is correct option. In question number 27, the time constant of an inductor is tau 1. When a pure resistor of R is connected in series with it, the time constant is tau 2. In first case, there is only internal resistance of the inductor, let's say that is R. And in the second case, external resistor capital R is connected, so total resistance will be small r plus capital R. We want to find the internal resistance of the inductor. Here time constant of LR circuit is given by L by R, so we can write tau is inversely proportional to R. So tau 1 by tau 2 is equals to R plus R divided by R. Cross multiply this. R tau 1 is equals to R tau 2 plus capital R tau 2. We want to find internal resistance small r, that will be R tau 2 divided by tau 1 minus tau 2. So option 1 is correct option. In question number 28, a coil of inductance 8.4 millihenry and resistance 6 ohm is connected to a battery of 12 volt. The current in the coil is 1 ampere at what time? We want to find the time at which current is 1 ampere. The current growth equation is given by I is equals to I naught into 1 minus e power minus t divided by tau. The tau for LR circuit is given by L by R, that is equals to 8.4 divided by 6 into 10 power minus 3. So tau will be 1.4 into 10 power minus 3 seconds, and I naught is given by E by R, that is equal to 2 ampere. We want I as 1 ampere, so 1 is equals to 2 into 1 minus e power minus t into 10 power 3 divided by 1.4. So 1 by 2 is equals to e power minus t into 10 power 3 divided by 1.4. Taking natural log on the both side, we can write minus 0.693 is equals to minus of 10 power 3t divided by 1.4. Solve this equation for t. We will get t is approximately equal to 1 millisecond. So option 4 is correct option. In question number 29, there are two batteries A and B having same EMF, but A has no internal resistance and B has some internal resistance. Let's say that internal resistance is R, and inductance is connected first to A. The energy in the uniform magnetic field setup is U, and then it is connected to B. The new energy in this case will be U dash. We want to compare U dash and U. Here energy stored in inductor is given by half Li square. So we can say energy stored is directly proportional to I square. But according to Ohm's law, I is equals to V by R, as the EMF or both the batteries are same. We can say I is inversely proportional to resistance. So IA is inversely proportional to simply external resistance, but IB is inversely proportional to R plus internal resistance R. We can clearly see that IB is less than IA, so U dash will be less than U. So option 3 is correct option. In question number 30, an EMF induced in secondary coil is 10 power 4 volt when the current breaks in the primary. The mutual inductance is 5 Henry and the current reaches to 0 in t is equals to 10 power minus 4 second. Current reaches to 0, that means I2 is 0. We want to find the maximum current in the primary before it reaches to 0. So I1 we want to find. Here we can write induced EMF is equals to minus m di by dt. So E is equals to minus m 0 minus I1 divided by dt. So we can write I1 is equals to E into delta t divided by m. E is 10 power 4, delta t is 10 power minus 4, and m is 5. So I1 is 0.2 ampere. So option 1 is correct option.